Hey all, welcome to Homeschool. Class 11 chemistry series is going on. We already started few chapters of class 11 and I am strictly following NCERT syllabus. See, based on this particular books, you will have to write various entrance examination. The national entrance examination for engineering like IIT, JEE, and various other state entrance examinations are also based on this NCERT syllabus. Okay, so we already completed the first chapter, that is basic concepts of chemistry, and started with the second chapter, structure of atom or atomic structure, where I am actually discussing about the atomic models. So in the atomic models, different scientists have tried to explain differently about how protons and electrons are arranged in the atom, right? So we already discussed about the Rutherford's model, Thomson's model, and we are in a process of learning Bohr's atomic model. But Bohr, before inventing his model, he studied two aspects. One was dual nature of electromagnetic radiation, and the other one is atomic spectra. So dual nature of electromagnetic radiation means our electromagnetic radiations, that is the visible light, IR, UV radiations, X-rays, all these are different electromagnetic radiations. So they have two nature. One is wave nature as well as particle nature. Wave nature we discussed and it was proved by interference diffraction, right? And particle nature we started studying, and this particle nature is best explained by black body radiation and photoelectric effect. Black body radiation was already discussed in the previous class, and in today's video we are talking about photoelectric effect. So we will try to learn what exactly we mean by photoelectric effect and how it can be a proof for telling electromagnetic radiation has a particle nature. Okay, so now see, a scientist called Hertz, and he has done a beautiful experiment, and that experiment led to the discovery of photoelectric effect. Let us try to understand what is that experiment. Okay, see, he took an evacuated glass tube. So what do you mean by evacuated glass tube? A glass tube without any gas. Okay, so you don't have anything inside the glass, and he took one metal plate as cathode, and this metal plate, you know what, this metal plate is made up of cesium metal, right? So this is actually a cesium metal. So you all know where cesium comes in a periodic table, right? So if you take the first group elements, you have lithium, sodium, potassium, rubidium, cesium, right? So cesium comes in 6th period, first group. Clear? So it's a very, very important element, is because it's a very reactive element. You know what? Its atomic size is very much big. So cesium is the largest element in the periodic table, I can say, in some sense, right? So can you all think of how many shells are present in a cesium? Definitely it is 6 shells. Our outermost electron is there in 6th shell. Okay, so that means outermost electron is very, very far away from nucleus. So why am I telling all this story about cesium? Yes, you will definitely understand this, and this is really very important to understand photoelectric effect, right? Okay, so such element has been taken as a cathode, right? So this cesium element has taken as cathode, and the other element, the other metal plate, it is not of cesium. Okay, so some other metal plate, actually this will act as a detector. This can act as a detector, and this is also made up of some metal. This is anode and this is cathode. Okay, so let me write here, this is cathode and this is our anode. Fine, cesium metal was taken as cathode, and detector was taken as anode. And here they fixed some ammeter. So this is your ammeter. So we all know what is the use of ammeter, right? It actually measures how much current is flowing in a circuit, right? Fine. So this is our experimental setup. And now when a light of certain frequency was striked on cesium metal, okay, so from outside I will just strike a light of certain frequency. So this is some light, okay, with some energy or frequency. Okay, so when you strike light of some frequency, you know what? He started observing electrons coming from the cesium metal, right? See, whenever you strike this cesium metal with some light, with some energy and frequency, you know, the moment the light strikes on the surface of cesium, the electrons started coming out from cathode to anode, and this is acting as a detector. So its work is to detect. It acts as an anode. Along with that, it is a detector. It will detect that electrons are coming from cathode to anode. Since electrons are flowing, definitely some amount of electric current you will observe in ammeter. So he started observing the more and more current as you strike a light onto a surface of cesium. So it may be because the cesium has ejected electrons. Because the electrons are continuously ejecting and they are moving, definitely that is responsible for the production of electricity. So you will observe some value in the ammeter, right? So this was the experiment done by the scientist called Hertz. Okay, so this is an experiment of photoelectric effect. So now, how do you define a photoelectric effect? It's very simple. Just observe the sentence that I am writing. Ejection of electrons. Ejection of electrons. From whom? From the surface. From the surface of metal. Cesium is an example of metal, right? When does the electrons can be ejected? They can be ejected only when some light with certain frequency is struck on the surface, right? So ejection of electrons from the surface of metal when light of certain frequency is incident, okay, or is striked on the surface of metal. Okay, so this can be a definition for photoelectric effect. It is just very simple. So whenever you strike the surface with some light with certain frequency, okay, each and every metal will have a fixed frequency. When you supply a light with that frequency, only then ejection of electrons can be observed from the surface of the metal, right? So this is what we call photoelectric effect, right? And he also observed few things from his experiment. So let me learn those observations, whatever the Hertz has observed during his experiment. The first thing was definitely some minimum amount of frequency must be struck on the surface, only then photoelectrons are ejected. Okay, say the ejected electrons I can call with the name photoelectrons. I can also call them as photoelectrons. So a minimum frequency is necessary for a light, okay, for a striking light to observe photoelectrons, and that frequency we will call it as threshold frequency. Okay, so here there is something called threshold frequency. So what is threshold frequency? It is indicated with the letter nu naught. Okay, nu is normal frequency, nu naught is called threshold frequency. So how do you define threshold frequency? The minimum frequency minimum frequency of light, of striking light, at which or above which photoelectric effect is seen. Photoelectric effect is seen. Okay, so this is what we call threshold frequency. Okay, you know, at all frequencies you will not observe this ejection of electrons. For a particular metal, there is a suitable frequency. There is a light with a suitable frequency. Only when you strike with that frequency, photoelectrons are ejected outside. And that minimum frequency we will call with the term threshold frequency. Okay, fine. And the second point is, as threshold frequency increases, okay, so as threshold frequency increases, say for example you have given more than required, say for this metal, okay, imagine this is a cesium metal, you know, to observe photoelectrons from the surface of cesium metal you require just say for example 100 hertz, you know, a light having a frequency of around 100 hertz, okay, but you supplied 150 hertz. Okay, you supplied a radiation, you strike the radiation which is having a frequency of around 150. Minimum how much is required? 100. Right? So 100 hertz is enough to observe a photoelectric effect, but you supplied 150. You have supplied the radiation than required, right? So this extra amount of frequency or this extra amount of energy will get converted as kinetic energy of electrons. Okay, so what do you mean by kinetic energy? It is nothing but velocity of an electrons. Okay, so the more energy having radiation when striked, okay, frequency more means what? Energy more, right? So whenever you strike a radiation with very much higher energy, then electrons will come out with high speed. Okay, so more than required when you supply, you know, the speed of an electron, ejected electron, can be increased. Clear? So that's why as mu naught increases, or I can say as energy of incident radiation increases, what happens? Velocity of ejected electron increases. Okay, so this is really a very, very important point. Velocity means what? I can say it is the kinetic energy of ejected electron can be increased, right? So this is one very, very important point. See, first point is, if you have to observe ejection of electron, you must strike a light with some minimum energy or minimum frequency. So that frequency we will call it as threshold frequency, and energy we will call it as threshold energy. Okay, so there is a relationship between frequency and energy, right? E is equal to h nu. So if frequency increases, energy of that radiation is more, obviously, right? Okay, so that was the first point. And later when you supply the radiation more than required, I mean more than threshold energy or threshold frequency, you know, that extra little amount of it is used for the ejection. That extra amount of energy, say 100 is required, but you supplied about 150 hertz. So this 50 hertz, extra 50 hertz of energy is used for increasing the speed of ejected electrons or the velocity of ejected electrons, or in other words I can say kinetic energy of ejected electrons will be increased. Okay, so that is your second point. And now third point is, as the intensity of radiation increases, this is also very, very important point. As the intensity of radiation increases, what happens? Number of photoelectrons ejected increases. So what do you mean by this point? So this is the third important point that you have to remember. As the intensity of radiation increases, so what is the difference between energy of radiation, or energy or frequency is one and the same here. Okay, frequency is directly proportional to energy. Frequency more means its energy is more. So as energy or frequency increases, kinetic energy of ejected electrons increases. Okay, then the next point you see, as the intensity of radiation increases. So what is the difference between intensity and energy, or intensity and frequency? Intensity is nothing but brightness. Okay, so what do you mean by intensity? Intensity is nothing but brightness, right? See here, frequency is related to, frequency or energy is related to color of radiation. Color of radiation. Say for example, okay, so you have a visible light, right? Okay, let me tell you here. You have a visible light. So visible light have 7 different frequencies, right? So violet, indigo, blue, whip gaya, right? So green, yellow, orange, red. So can you tell me which of them has higher frequency here? Definitely violet light has high frequency. I can say violet light has high energy. Here high energy or high frequency means one and the same. Okay, red light has less. Okay, it has less frequency, right? Say for example, when I supply red color light onto a metal, maybe the frequency is not enough, you will not observe ejection of electrons. When I supply yellow light, then also the photoelectric effect will not take place. But when I supply violet light or indigo light, since the frequency is very high, maybe that frequency is enough for this cesium metal to eject the electrons. So you know what, when I supply a violet light, when I strike this metal with a violet light, automatically you will observe photoelectrons. But when I supply a light which is having frequency more than violet light, then also you will observe this photoelectrons. Okay, say when I supply more frequency having light, actually the speed of ejected electron increases. That's what this point means. Okay, and this point I'm talking about intensity. See, violet light I'm striking, photoelectrons you are getting. Okay, and here if I supply dull violet light, okay, intensity means brightness. Okay, so when very much dull light, I'll make the source dim. Okay, you can just think of the torch light, dimmer light and brighter light, right? So when the light is dim, I will say intensity, violet light itself, but it is dim, I say intensity is less. But when the violet light is bright, when bright violet light when I supply, it's violet light only, it's having the same frequency. Dim violet and bright violet. Dim violet, bright violet. Both have same frequency. Both have same frequency. Violet light, dim or bright, same frequency. But intensity of dim violet is less. Okay, intensity is less. Here bright violet, intensity is more. Dim means less intensity. Okay, so bright means more intensity. Clear? So when brighter violet light I supply, more number of electrons gets ejected. Okay, so if this light is a bright violet light, what happens? More and more electrons ejected, but the speed is same. Okay, your speed is related to frequency, your number of electrons ejected is related to intensity. This is what I meant to tell you. So here intensity is different, frequency is different. Okay, so intensity is nothing but related to brightness. So the brighter light, more the brighter light you strike on the surface, more and more electrons gets ejected. But when more and more frequency energy radiation, when you strike, the speed of electrons increases. So these 2 points are very, very important to understand. Clear? So these are the observations that Hertz was observed when he was doing this experiment, right? And you know what, and this is what proves, this proves the particle nature of electromagnetic radiation. Say if you consider wave nature of electromagnetic radiation, you know what, as the intensity increases, actually intensity you will talk only for the particles, okay? Dim or brightness is related to particle nature, it's not related to wave nature. So here came a matter of intensity, so definitely the entire concept focuses, it tells about the particle nature of electromagnetic radiation. Okay, so if it was a wave, this variation will not be there. Just as you increase the energy, you would have got more and more electrons with high speed. Okay, but here number of electrons ejected was dependent on intensity. Okay, so intensity is the one which you will talk only when something is moving in the form of particles. Say if more brighter light means more photons, more particles are striking. Lesser dim light, when you focus here, less number of particles are striking. That's what the meaning is. Okay, so wherever we come across the intensity, it means that we are talking something about the particles, not about a wave, right? So this is what the proof for telling that the radiation here is acting like a particle. Radiation, this striked, the radiation is made up of small particles, and each particle is called as quantum, right? So this proves that, the photoelectric effect is based on the particle nature of electromagnetic radiation. Okay, so everything is fine. And the same thing was explained differently. I mean, the same concept, but explained in a different way by Einstein. So now we are learning about Einstein's explanation related to photoelectric effect. Actually, for his explanation related to photoelectric effect, he got Nobel Prize in 1905. Okay, and actually much before this, he has discovered theory of relativity. He discovered the famous equation E is equal to mc square and so many other things. Okay, but he didn't get Nobel Prize for those particular things, but he got Nobel Prize for giving the best explanation for photoelectric effect. Okay, so definitely we must understand what Einstein explained about this photoelectric effect. Clear? See, photoelectric effect was discovered by Hertz, but it was very nicely explained in an acceptable way by a person called Einstein. So let us learn that Einstein's explanation for photoelectric effect. See guys, I summarized Einstein's explanation in the form of these points. See, you can look at the first point. No time lag between striking of light and ejection of electrons. So what do you mean by this point? There is no time lag. That means there is no time gap. Okay. Say for example, if this is your metal, the moment you strike this surface with a minimum amount of energy, this radiation must have minimum energy, otherwise electrons will not be ejected. So the moment you strike some suitable radiation onto this, immediately electrons are ejected. There is no time difference. Okay, so the moment you strike, you will observe the electrons. So that's what we mean by no time lag between striking of light and ejection of electrons. Fine. And next point, light is, he told that, see, there's no time lag between striking and ejection means, it means that he told the light is made up of particles, small particles. He called those particles as photons. Okay, see, Planck introduced his quantum theory and he called those particles as quantum, right? But here the Einstein says that if it's a visible light, the moment the light strikes, the smallest particle he called with photon, and same thing, each photon has certain energy and that energy is equal to h nu. Okay, so as frequency increases, the energy of that radiation increases. Fine. And then energy of striking light is directly proportional to kinetic energy of electron. Okay, say for example, as you provide more energy than required, okay, say that extra energy that you have provided, no, that will get converted as kinetic energy of electron. So kinetic energy of electron and energy of striking light is directly proportional to each other. And then kinetic energy of electrons do not depend on intensity of radiation. This is very important. Okay, so kinetic energy, speed of electrons doesn't depend on brighter or dimmer light, right? Brightness is nothing but intensity. Okay, it only depends on the energy of radiation. Okay, so minimum energy is necessary to observe photoelectric effect. More than that, when you supply a energy, then more kinetic energy you would observe, right? So it only depends on the frequency or energy. It doesn't depend on brightness of light. Okay, and next point you can observe, more the photons strikes onto a surface, more the photons means more intensity. Brighter light will have more photons actually. Okay, so more the photons, I mean, once your energy criteria is satisfied, once you supply that minimum energy to observe a photoelectric effect, after that, when more brighter light you supply, you know, more photons when they strike, more electrons gets ejected. Indirectly, more the frequency, more number of electrons ejected. But the speed of ejected electrons, kinetic energy of ejected electron depends on frequency, whereas the number of electrons ejecting from a surface depends on the intensity. Okay, so usually one photon, when it hits on the surface, one electron comes outside. This is when your limited criteria is satisfied, when your necessary criteria, what is the necessary criteria? Minimum amount of energy must be there for the radiation. So if that is satisfied, once the electron started emerging outside, ejecting outside, then the brighter light, I mean more photons, when they hit, more electrons will come out. So after that, it's like one photon on hitting, one electron will come out. Okay. So this is the observation. These are the key points given by Einstein about the photoelectric effect. And now the main thing is he has given one major equation. He can tell the entire photoelectric effect in one particular equation. That equation we will call it as Einstein's equation. Okay, so that is very important. I am writing now Einstein's equation for photoelectric effect. PE means photoelectric effect is equal to, you see, E or just H nu is equal to H nu naught plus half mv square. Okay, so what do you mean by this point? Imagine if you have a certain energy for the radiation, okay, so this is the total energy of a radiation, so more than required, some minimum energy is necessary, beyond that you have taken some more extra energy, okay, so much higher frequency than required you took, so you know this is the total energy of a striking radiation. Say among the total energy, some energy is used for the ejection of electrons. So what is that energy? H nu naught. You see, threshold frequency. This is the total frequency of radiation. Among the total frequency, some frequency having radiation, some energy is used for the work to done, which is the work that is going on, ejection of electron. So remaining extra energy has converted as kinetic energy. Okay, so this half mv square is the formula for kinetic energy. Okay, so actually this equation I can also write in this way. So E is equal to, E means what? Total energy. Total energy is equal to W plus kinetic energy. So this is a simple way of telling, this is elaborate way of telling. So what is W? Work function. This is also called as work function. Okay, so work function is nothing but it's the energy or the frequency that is necessary to observe photoelectric effect, to observe the ejection of electrons. Okay, plus kinetic energy. So among the total energy of a radiation, some amount is used for the ejection of electron and the extra amount is converted as kinetic energy. So total energy is equal to energy that is used for ejection of electron plus kinetic energy, right? So that is mathematically represented like this. So h nu is equal to h nu naught plus half mv square. You can write this in terms of lambda also, right? Say it's according to the information given in a question, you have to use the suitable formula. Numericals can be asked on this. Say if they give you the total frequency and this is threshold frequency. Okay, so when they give you total frequency, threshold frequency, something like this, information relating to frequency, you can use this. But when they give you information relating to lambda, okay, so instead of frequency, they'll give you lambda. So what's the relation here? C is equal to lambda nu. We all know this. So nu is equal to C by lambda. So when you have information relating to lambda, then I can write it as Hc by lambda is equal to Hc by lambda naught, threshold wavelength, plus kinetic energy, that is half mv square. So this is Einstein's equation in terms of lambda. This is Einstein's equation in terms of frequency. This is Einstein's equation in terms of just energy. Okay, clear? And this h nu naught can also be called with work. Okay, so W means what? Work function. What do you mean by work function? The minimum energy among the total energy, it's the minimum frequency or minimum energy that is required for the ejection of electrons. Okay, so all the three equations are very, very important. So he summarized the entire photoelectric effect with this one particular equation, right? So this is what the concept on photoelectric effect. So these three equations, try to remember. Now we will try to solve few questions on photoelectric effect. Look at the first question here, guys. The threshold frequency nu naught for a metal is this much. Calculate the kinetic energy of radiation of frequency is equal to this much. Hits the metal. Okay, kinetic energy of the ejected electron is what you have to calculate actually. So what is given? Nu naught is given, that is 7.0 into 10 power 14 second inverse. So second inverse is nothing but hertz. Okay, so units you must be aware of. And nu is given, that is 1.0 into 10 power minus 15 second inverse. Okay, so they are actually asking you to calculate kinetic energy of ejected electron. So what is the Einstein's equation for photoelectric effect? So it is h nu. It's in the in your question, the information is there in terms of frequency, no? So take this equation, h nu is equal to h nu naught plus half mv square. So you need to calculate kinetic energy. This is what this term you need to calculate. So what's your formula? H nu minus h nu naught is equal to kinetic energy. Just a rearrangement. This I brought it that side. So you can take h common, right? So nu minus nu naught is equal to kinetic energy. So h value we all know, right? H value is equal to 6.6 into 10 power minus 34 joules second. Okay, so this is the Planck's constant's value that you need to remember. So put that value here, 6.6 into 10 power minus 34 nu. Okay, so what is nu? 1.0 into 10 power 15. 1.0 into 10 power minus 15, right? Minus, what is nu naught? 7.0 into 10 power 14. So how do you subtract? We have learned subtraction of scientific notation, right? Actually, it is plus. Okay, so it's plus 15. So I can write 1.0 into 10 to the power of 15 is nothing but 10. Okay, so I'll bring this point here. So when I bring this point here, 10 into 10 power minus 1 into 10 power 50. So it becomes 10 into 10 power 14, right? So it is 10 minus 7 you have to do. So 6.6 into 10 power minus 34. 10 minus 7 is 3. So 3 into 10 power 14. right? So you just have to multiply. 3 6 are 18, right? So 3 6 are 18 plus 1, 19. So it is 19.8 into. So here 10 power minus 34 into 10 power 14. So minus 34 plus 14. So it is your 10 power minus 20. Okay. So the unit for energy, kinetic energy is energy. Unit for energy is joules. So we commonly calculate energy in terms of joules only. And there is another unit for energy, that is electron volt. Okay, so either you can calculate energy in electron volts or you can calculate in joules. So there is a conversion factor between joules and electron volt. Try to remember this. This is very much helpful for you. So 1 electron volt is always equal to 1.6 into 10 power minus 19 joules. Okay, say in whichever the units they may ask, you just have to convert and show it in the answer. So that's all about the question number 1. And now let's go for question number 2. A light whose frequency is equal to 6 into 10 power 14 hertz is incident on a metal whose work function is 2 electron volts. See, energy, work function, they have given it in electron volt. The maximum energy of electrons emitted will be, see, they are asking energy of emitted electrons. That means they are asking kinetic energy of electrons is question mark. So what is given? Work function is given, that is in electron volt, 2 electron volt. And another thing, a light whose frequency is equal to frequency, just normal frequency, nu is given, that is 6 into 10 power 14 hertz. Okay, so they are asking kinetic energy. So what is that you have? H nu is equal to H nu naught plus kinetic energy. So this H nu naught is nothing but work function. Yes or no? H nu naught is nothing but your work function. Work function value, it is directly given. But you see, it is given in electron volt. Convert this in joules. How do you convert this in joules? I gave you conversion factor. 1 electron volt is equal to these many joules. So 2 electron volt in 2 into 1.6 into 10 power minus 19. Right? So how much do you get here? 2 6 are 12, 2 1s are 2, 3. So 3.2 into 10 power minus 19 joules you will get. Okay. So your work function is this much. We just have converted electron volt into joule. Okay. So this H nu naught is directly given for you. That is this much joules. It's directly given. So what you have to do? So you have to do H nu minus work function. If you do, you will get answer for kinetic energy. Okay, so H nu, H value you know 6.6 into 10 power minus 34 into nu value they have given 6 into 10 power 14, right? Okay, so this minus work function, calculate in joules. So you converted just now to 3.2 into 10 power minus 14 joules. Okay, so if you do this, you will get your answer in joules. Clear? Is that clear? So this was one of the question from previous year NEET examination. Actually, I didn't give you the option, right? I just gave it as a normal question. See, this is the process of calculating. Actually, in the option, the answer was in joules. That's why here the work function which was given in electron volt, no, I converted to joules. Okay, so if your answer is in joules, then definitely this must be converted in joules and then take it in a problem to calculate. Say if your answer they asked you in electron volt, then this value as it is you have to take, and this value, this H nu, calculate separately. You will get your answer in joules, no, that you convert to electron volt. Okay, so if they are asking the answer in electron volt, take this value as it is, W value as it is. Now H nu on calculating you get the value in joules, no, that you convert to electron volt. Conversion factor is this. So you have to be careful in which units they are asking the answer, especially for the competitive exams. Okay, so I think just here we calculated our kinetic energy in joules. Okay, so post your answer in comments. Let us see whether you have given correct answer or not. Okay, also convert that answer in electron volt. Okay, so I want two answers here. One answer in joules. Okay, just on doing this you will get. The other answer I want in electron volt also. Okay, so I want kinetic energy value in electron volt also. So two answers, one in joules, the other one in electron volt. Both answers you have to post in the comment box. So that's all about photoelectric effect and the type of problems that can be asked on photoelectric effect. So say with this we have completed dual nature of electromagnetic radiation. Okay, so what's the final conclusion here? Whenever the radiation travel in the atmosphere, when it propagates, it will travel in the form of a wave. But when it interacts with matter, say when some absorption and emission of radiation is taking place, then it happens in the form of particles. So this is what the final conclusion for dual nature of electromagnetic radiation. So depending on the situation, it behaves like a wave and the radiation can also behave like a particle, right? And this is a very, very important idea one must have to understand the structure of atom further. Clear. And the next aspect we are going to study is about atomic spectra. Okay, so Bohr has also studied about hydrogen spectrum. Based on his observations on hydrogen spectrum, he gave certain postulates regarding the structure of atom. So all of them we will discuss in the next class. Thank you so much. Do subscribe our channel to learn the concepts in an easiest way and in a detailed way. All the best.